Hello, everybody. Today we're going to solve a second order linear homogeneous differential equation with a constant coefficient. So let's define each term and what it looks like. Well, first of all, let's look actually at how all of this look like. This is the general form of what I'm talking about. Look, that's how it looks. Now, what's a second order? Well, second order is we can find that out by the highest derivative, or you can say prime in the equation. See, y double prime. That's how I know it's second order. That's the highest derivative. How do I know it's a linear? Okay, you see the coefficients are functions of x, a of x, b of x, and c of x. That's also how I know it's linear. How is it homogeneous? That's how you're supposed to say it, I guess. Well, this equation has the d of x has to equal 0, or it cannot be homogeneous. That's what a homogeneous means. Have to equal to 0. And with a constant coefficient, a, b, and c are constants. Okay. Well, there are three cases in the whole. Well, the three cases I'm gonna explain, and I'm gonna explain how you find which case is which. Well, the first case is two distinct real roots, and how you find that is when you get your equation, you plug it into this equation right here, and if it's bigger, the outcome is bigger than 0, you know for sure it's going to be distinct real roots. And by the chain rule, that's how we transfer our differential equation to a quadratic equation. You go over here, you know, the y double prime is r squared e rt, etc., etc. You put it all together right here. Then what you do is just take out the e to the power of rt and divide it out. You get your equation right here, the quadratic form. I solved this equation in two different methods. One for me was much simpler. The other one I just had to do just to make sure it looks. You get the point of what I mean. Well, my personal method, or actually, let me explain the quadratic method. Put you see r squared minus 3r minus 10. That's what I got. Transferring this using the chain rule to this quadratic equation. You look at this side right here. This the quadratic equation. I just plugged in the numbers and solved, and I got to this point where I got one root is 5 and the other root is -2. And when you have that, your equation is going to be c1 e to the power of rt plus c2 e to the power of rt. Well, you plug in the numbers you already found, which is -2 and 5. That's the equation. You just plug it in, and that's the general solution. The second way I did it to make sure was I saw the quadratic function, and it was really easy to factor, and that's what I did. You see, here I factored it. I got r minus 2 and r plus 5. Just transfer it to the other side, and you get all that. Okay, now I also got the same solution here. Just plug it into the equation you already have, which is y of t equals c1 e to the rt, etc., etc. Now, that's how I know it's two distinct solutions. I got two answers. Now, look, I'm going to look at a little bit more complicated case, which is repeated. We have a repeated solution. See, to find that case out, the equation here is b squared minus 4 times ac. I did the exact same thing. The equation I have is y double prime minus 6y prime plus 9 y equal to 0. That's how I know it's homogeneous. Now, I did it also in two different ways just to make sure. After I made it to a quadratic form, I did it in a quadratic equation. And after all that math, I got 3 repeated. I got both roots at 3. And that's the equation when you have a repeated, a C1e r to the power of RT plus C, then you put a TE, that's an extra T right here because it is repeated, to the power of RT. Just plugged in the 3's where they belong in the R's. And that's the general solution. My way too also did the exact same thing as the first method, where I just factored it. I got R minus -3 twice, and I said R equal 3 repeated, and used the same equation, just plugged in the numbers. And that's also the general solution of it. Now I'm gonna go to the third case, which is a little bit more complex, but it's not really hard. You get complex roots. Now, my equation was y double prime minus 2y prime plus 2y equals 0. Unfortunately, I couldn't factor it here. I don't think it's possible to factor it using the methods I've used before. Now, I had to use the quadratic equation. And I actually checked, that's how you also check, it's a complex root by this equation, b squared minus 4 times ac. And I checked it, and it's less than 0. Now, when I put in the quadratic equation, just did the math over there, really simple. But what I got here was a square root of -4. And to square root a negative, you get an I, an imaginary number. So what I got was 2 plus negative, 2 plus or minus 2y over 2. And just divide that. And I got 1 plus or minus I. So if you end up in this situation when you have an a plus plus or minus bi form, your equation is going to be c1 e to the power of at cosine of bt plus c2 e to the power of at again sine bt. It's kind of repetitive. It just, the thing is, the first one you got a cosine, the second one you got a sine. What's the you know, the a is the 1, but what's the b? It's not going to be the I, because you always know the coefficient here is going to be there's always a 1, so the coefficient was 1, and I just plugged in the 1's, and that wouldn't change anything. It was just take away the r's, and that's the equation right here. That's the general solution of that equation also. So that's the 3 cases: 2 distinct roots, double repeated roots, and complex roots with imaginary number.